All right, we're going to go ahead and get started. Before I welcome any of our guests, I'd just like to invite everyone who has not already done so to please subscribe to our YouTube channel, Magnimind Academy, where we upload recorded sessions of these talks so you can watch them later. You can also comment any questions you have on YouTube, or just let us know about what you think about today's talk in the comment section below. Now I'd like to welcome Veysel Kocaman. We'll be presenting an NLP workshop focused on the state-of-the-art clinical named entity recognition. We try to find speakers like this who can enrich our learning programs and just give a different perspective other than to go along with our data science education. These programs range from focusing on the fundamental skills of data science all the way to helping start your career change into the industry. And our goal at Magnimind is impacting as many careers as we can. Really, this is just one way that we do so. Kocaman joins us as the lead data science of John Snow Labs, where he primarily uses skills from this workshop to do his daily job. John Snow Labs focuses on implementing more AI in healthcare, and this has actually been a theme of all of our different talks these last few weeks. For this role, Kocaman has worked for over a decade at different data science related jobs, both in research and in teaching positions. Veysel is an educator in his own right, but he has put a great deal of time into his own education. He earned his master's in operations research from Penn State and is currently working on his PhD in computer science from Leiden University. We at Magnimind are extremely excited to host him, and we'd like you now to ask to give your full attention to Veysel Kocaman.
Thank you very much, Thomas, for the great intro. I really appreciate it. Hello, everybody. I'm Veysel. I'm based in Netherlands at the moment. As Thomas just briefly explained, I'm a lead data scientist at John Snow Labs. In the meantime, at John Snow Lab, this is what we do day-to-day basis, like training new NER models or assertion models that I'm going to cover briefly to solve real-world problems. I'll start explaining Spark NLP at first and how we do, how we start, like how we build our NER algorithm and then how it works, and briefly explain the history of NER algorithms at the moment, and then do some hands-on coding, and then answer some questions if you have any. So Spark NLP is an open source NLP library released in 2017, and right now it has around 4K daily downloads from PyPy, like a Python site. We already support many other languages like R, Java, and Scala, so we support 4 languages. We also download, the monthly download is around 100K, and we about to hit 1 million soon in total. So the goal was to be able to create a single unified NLP library that would require no other dependencies other than Spark itself. And it should also work on the cluster. So there was no other library that could run on Spark clusters, by the way. And then all the other NLP libraries like Spicy, Jansim, TextBlob, NLTK are doing amazing things, but they are not, we usually skip one language to another to accomplish certain tasks, depending on the features they provide. And we also wanted to take advantage of the transfer learning and implementing the latest and the greatest state-of-the-art algorithms that, for example, for a certain NLP task, we wanted to pick up some paper and then try to implement it inside Spark NLP, like through Scala, and then support it into Spark NLP. According to recent surveys for the last 2 years, it's the most widely used NLP library in industry. And it's widely used in clinical industry, by the way, like healthcare domain, but we also have many other clients that are already using. Apart from that, there are many other big companies like Microsoft and Google already using Spark NLP. We have some contacts over there that we are aware of they are using it. And we get some questions and then some feature requests from them as well. We have a full-time development team. We are releasing a new version every 2 weeks. In just 2019, we released 30 new releases. So we have I covered most of these topics in one single blog post, like a Spark NLP Foundations and Basic Conference. It's the first blog post that we wrote to explain everything inside Spark NLP. Maybe you can just read that one. It's like a 15 minutes read to cover everything, to see what's going on in Spark NLP. So let's talk about the modules. We have public and healthcare modules. Healthcare modules are licensed, which is not free, but the publics are totally free. We also have another library which is called Spark OCR, because everything starts from like PDF or images when it comes to clinical text. So electronic health records or medical records are usually in not in plain text format. So we use Spark OCR for that, but I'm not going to cover that today. On the right-hand side, you see the public modules. We are supporting 22 languages by using the same NER architecture, which is another nice point to underline, by the way, because we can switch one language to another easily as long as we have the relevant word embeddings or the word coverage to accomplish certain tasks in NLP. We have some deep learning based sentiment analysis or document classification algorithms or pre-trained models that you can just plug and play. So instead of trying to build your own pipeline, you can just download any pre-trained pipeline and then just feed your data frame. And then you end up with the latest like state-of-the-art results using the various word embeddings, including Glow and the latest cool kids in the NLP town like Elmo, Bert, Albert, XLNet. So we all support them, and you can just use any model like a building blocks, like a plug and play. On the left-hand side, you see clinical versions, like clinical models. We have 4 main clinical models. We have more than that, but let's just cover 4 of them, like clinical NER, extracting clinical entities. We have around more than 20 different NER models, clinical NER models, which means like pre-trained on certain clinical NLP data sets that is being used in clinical NLP challenges like IQ-BQ or N2C2 data sets, we call them, like anatomy NER, PHI NER, pathology NER, etc., to extract the meaningful chunk given the task. Clinical entity linking is assigning some SNOMED, RxNorm, or ICD-10 codes to these entities detected through clinical NER models, and is detecting the negativity scope of each word, like each, not each word, but each chunk detected through clinical NER model. So assertion is very important model in healthcare domain. So it's like if the clinical node is talking about patient's father, not the patient itself, we need to know that information so that we can assign different features, like create different features accordingly. Or if it's not there, we can just filter out those symptoms maybe. For the identification, we remove or mask the sensitive information. According to HIPAA rules, safe harbor approach, we need to hide or conceal some of the information. These are called sensitive information. We need to de-identify or obfuscate. Obfuscate means like replacing with the fake names or entities. So we also have some pre-trained models that you can plug and play and then combine with the public models. And we have some medical terminologies we already have. We are trying to create our own BERT embeddings, and then we have our own clinical Glow embeddings that we use nearly everywhere on NLP, clinical NLP site. So what is Spark NLP? Let me show you how it works. On the right hand side, you see the syntax from 3 different languages, Java, Scala, and Python. On the Java, as you may have realized, like the syntax is very similar, given the difference of these languages. Like Python is a lot different than the other languages in terms of the simplicity of its syntax. And so which means that you don't need to be afraid of skipping from one language to another when it comes to Spark NLP, because the syntax is very similar between the languages. We also support R. So we have, as I mentioned before, we have active development and support team. And when you try to deploy your code over the cluster, you don't need to change any single line of code. So you can build your pipeline on your local to parse 5,000 documents, and then now you want to parse 1 million documents on a cluster. You don't need to change anything. You just change the Spark's Spark context or Spark session initialization parameters to point to the master or slave nodes. But the rest of the code will be same. And Spark, even on a single mission, Our experiments show that Spark NLP runs faster than the other NLP libraries due to Spark's own shuffling, caching, garbage collection, or some kind of memory management features that the other conventional libraries doesn't support. So let's get inside a little bit further. As I mentioned before, it's like a building blocks. So you pick up some models according to your use case, and then you run, you like append each other in a pipeline, and then you can save your pipeline and move anywhere you want, or save or deploy any cluster that you want. So, for example, in this example, you feed just one single text column, data frame, text column. For example, you read 1 million txt files from a folder through read whole text command from Spark itself. And then now you have one data frame on a text column. The content of each text files would be in one row with the file names. And now you want to get, for example, word embeddings of each word, or get the clinical entities, or do some classification. So you can just like start appending document assembler, which is the gateway to Spark NLP. Everything starts with document assembler. We have an article about that, by the way. You can just check how it works. Why do we need it? It just handles the basic cleaning. And then sentence detector, like splitting the sentences and then getting the tokens, and then applying some token-based normalization, like cleaning the unwanted chars, or dropping some punctuations, etc., or some digits, and then getting word embeddings from each one. So every module creates new column given its role. So at the end, we have as many number as columns that we use in our pipeline. Like if we can just append NER here, like a named entity recognition model, and then it will have NER column as well. And then you can just drop all the other columns, or you can just use the one that you need. So how do we solve problems? Why do we need NERs in healthcare? So let me briefly explain how a classical NLP pipeline works in healthcare domain, how to solve this problem at Johnson & Johnson. So we start with the electronic health records. It would be in PDF or image, or just X-ray, maybe some DICOM format, maybe. So we use Spark OCR to extract the text at first. If we also need to de-identify the information, like to hide this information from the developers, from the other people working in other downstream tasks, we also de-identify. But usually we start with the identified text. Skipping Spark OCR, assume that we just start with the TXT files already de-identified. Now we start processing, like our goal, assume that we want to extract those entities. Because why do we need this, by the way? It's like a clinical decision support system. It's the part of the clinical decision support system. So we want to extract knowledge, usable knowledge from these garbage data, because it could be kept in any format, like just free text, or just some Excel sheet, or some hand notes. So it could be anything in any format. So the goal is to be able to leverage the power of that hidden text. Otherwise, we already have some numerical columns that we can use to build some machine learning models. But when it comes to text data, which is already hard to understand by regular people, yeah, even though you know English or your own language, when it comes to medical language, it's very hard. So that's why we need to train new models. And as you know, NLP is an ultra domain specific field. So we usually end up training our own models. So if the problem is extracting those entities, we have our own annotator, like built on top of Label Studio. So we have our clinical physicians or domain experts that could do some annotations given the task. If the task is extracting some metastatic related entities, we talk to them, like as a developer, we get together and then talk to the annotators, like the physicians. We usually work with 2 to 3 different medical doctors in any healthcare projects, by the way, at Johnson & Johnson. And then we try to make sure that they understand what to extract, because they also need to understand how our NER algorithms works. If they just highlight everything, it doesn't work because our models doesn't work that I'm going to explain. So they also try to let the model find the differences between various entities. So they annotate, they just highlight some parts, they upload TXT files, and then they highlight some parts, like they assign this is disease entity, this is modifier entity, this is site entity, this is modifier, etc. And then we start to train our models using our clinical NER model, which is called NERDL. So everything starts with the problem itself. Yeah, even the annotation starts from the problem itself. So it's not just a one single universal NER model out there. So every time we already have more than 20 pre-trained models that could be useful to extract some basic features. But when it comes to solve some problems, you always need to check your objective. Like assume that we want to predict if a patient would develop a metastasis on a certain site. So we start with annotating our own data given this problem. We say that, okay, so we need to know if this patient would develop a metastasis. So we need the certain sites like the lungs, the liver, bone. Okay, and then we need to know if it's absent or present or related to family members, etc. Because there are sometimes more than 1,000 documents per patient spread around for the last 10 years. For example, if there's a patient visiting the oncology clinics for the last 10 years, they might end up with producing thousands of documents per patient. So that's why it's hard for human coders, human abstractors to extract information so that the clinicians or the data scientists would develop some models by using that data hidden inside those thousands of documents. So we can either automate this process by extracting those entities, finding the dates of metastasis, or we can also predict something. So it's not just predicting. So we can also use NLP to automate steps that will be done by human coders. So for example, for the specific case, we can just take the clinical documents, detect those entities through NER after annotation, extract some features, and then apply some feature engineering steps. What could be those? So according to our problem, so we need to predict something. So we need to find the features that could be useful. If you just feed thousands of documents into pipeline and then try to classify those tags, it doesn't work because there will be a huge sparsity in your data set. So you need to find the relevant sentences that could indicate this phenomenon. So that's why we need to create some handcrafted features, like the number of diseases detected in the last 30 days. So how you can find those diseases, you can throw away some pre-trained NER model to detect the clinical problems or tests. You can also remove the hits, like remove the entities that would be related to patient's relatives, like the father or sons, etc., not the patient itself. Those are all the relevant features that could be useful to build this prediction model. I think you already covered what I meant, so I'm just skipping. As I said, this is just a part of clinical decision making cycle, like clinical decision making system. We are trying to support the clinicians to make their life easier and faster and better, actually, so that they can use their own knowledge and do things faster. Because we are not trying to replace, we are trying to automate some of the repetitive tasks that they already do. If they can, if a human can do this, machine can do that as well. So anything that needs to be done more than once, any repetitive task that needs to be done more than once can be automated through machine learning. Machine learning is not just predicting, but also automating some stuff. Because when we usually see that annotators annotate some clinical documents, and then after a while, we start to pre-annotate the rest of the corpora according to their annotations. They realize that the model is not thinking, but assigning some labels as if they would assign. So they say that, okay, this is doing exactly what I would do. So because we trained the model given their inputs, so we are just trying to replicate what how his thinking frames, like solve that problem in a real world. This is where that smart algorithms comes into play to find that pattern inside human brain. So we are throwing away like all these models to solve this problem and then help the clinicians make that decisions faster and better. So as I said, everything starts with clinical NER, which is the topic of today, because it's the minimum meaningful chunk of any clinical text. The importance of NER might not be that much in any other domain, but in healthcare, it's very important. It's everything builds upon clinical NER models, like named entity recognition models. We have many other models that has nothing to do with NER, but when it comes to extract some knowledge, to get a sense of what's going on inside the document, we start with clinical NER model, and then use the other models. The other models use the output of NERs as an input, so that it could assign something instead of dealing with the entire text. They use like the other models, this entity linking, assertion status, and the identification, use the output of NER model to assign some status. If the fever and sore throat is a problem entity coming from NER, assertion status try to find if it's absent or present, given the text, given the sentence that chunk lives in. So that's why NER is very important and highly valuable when it comes to solve some problem through data. This is some of the examples that we just got the snapshots for certain NER models in licensed models. The left-hand side is the problem, test, and treatment entities, which is called clinical NER in Spark NLP. All these models are trained on clinical NLP challenges. Clinical NLP challenges, like every few years, there are some clinical NLP competitions running with several universities in the United States. And like some, for example, this one is coming from 2010 I2B2 dataset. The posology NER, which is responsible for extracting 7 different entity types from a context, like posological entities, medication-related entities, dosage duration, etc. This is coming from 2010 plus 2018 medication dataset. Anatomy NER is another. These are all annotated by researchers, which means that these are clean. So we train these models to prove, to see, to validate our approach, to see if it's doing good. I'm going to share some results which we are doing good, given their state-of-the-art results. And then, so which means that you can just plug and play those models without further ado. And then you can use the same architecture to train your own models, which I'm going to do that today. Let's compare what we do with AWS Medical Component. It's the closest competitor might be, not the competitor, but a similar results that you can get from AWS Medical Component API, which is not free, of course, and they charge per document. When we compare, we do a little bit better than what they do, even though we use the same data set, but we enrich our posology model with some OpenFDA data sets. When we first created this model, like for the 2010 I2B2, we got 85.81. Right now we are around 87, which is the state of the art, by the way. And as you can see, AWS, like we have some more hits compared to AWS. We already run a large scale comparison, and we are going to share with the public soon. Right now we are trying to validate our findings. Let's talk about the NER benchmarks. So we try to, as I mentioned, we try to get the best out of that. So we are using scarce CNN by LSTM architecture to accomplish that. And right now, state of the art is 93.5. We have 93.3. I think I have a similar slide in the following part. But right now, what we get is just on the test F1, which is an unseen data set, we have about 93, which is in top 3 of state of the art, and it's in production. It's not just on papers. So you can just use GPU as well without doing anything. You just start the Spark session with GPU support. like Spark NLP start with GPU. There's a single command like GPU true, which I'm going to show you today as well in Colab. And you can use any word embeddings with your data, and in a few minutes and few lines of code, you will get some decent results in Spark NLP NER models. By the way, this is public. So we use the same architecture on public and clinical models. On the clinical models for NER, we have our own data set, which just licensed users can use. But on the public side, you can use that NER architecture with your own data or any public data set to accomplish what you need without changing anything. Yeah, I'm talking about this list. Like nlpprogress.com, which is maintained by Sebastian Ruder. So like the latest rankings for each NLP task. And when we talk about NER task, the state of the art, according to CONNL 2003 benchmark dataset, 93.5, and we are 93.3, and it's in production. So this is like that orange part is our algorithm. And then you can use that algorithm with any embeddings that you want, Bert, Elmo, Glove, which will support many different algorithms, many different word embeddings that you can use. And we implement that paper, like 2016 Nichols paper, and it's still doing really good. So what's happening inside NER models? So let's talk about a little bit about its history. So it all starts with the classical approaches at first, like rule-based approaches, because as a human, when we look at document, we can understand those entities given our previous experiences, right? So we can understand if it's a people mentioned over there, if it's a problem mentioned, if it's a city mentioned over there. So which means that there could be some, we can just create some rules, create some features, and then train a classical classifier. And it works well. It surprisingly works well, by the way, classical approach. And then machine learning comes into play and then change everything, like jump from 50% to above 90%, given the rule-based approaches. So you don't need to write tons of if cases. And then deep learning approaches, which is the subfield of machine learning. And then there are some hybrid approaches, which is using machine learning plus deep learning approaches. So this is the paper that we used. And when it's first published, when we do this comparison like a year ago, it was still doing best out of all. So which means that we are still in the game. By the way, we are not just using this paper, we are also using some modified components from this. Like instead of their own LSTM, we also use our own LSTM implementation inside TensorFlow. By the way, Spark NLP has its own, has a TensorFlow wrapped in, like shipped with the library when you download, when you install. So you don't need to install TensorFlow in addition. And it works with 1.15. And everything that we accomplish on the backend runs through TensorFlow. So we have some graphs that we implement, and then when the number of classes differ from case to case, we change our graph, which I might cover today, but it's very easy. And then you can just run that onto your own problem. So these are the latest benchmark that I want to share. These are all clinical NER data sets. State of the art, these are the state of the art results from other Glove and word embeddings, not the BERT approaches, because BERT NER models, word-based NER models are not trained in a way that you can imagine. It's like another end-to-end training, not using like the BLSTM or deep learning approaches that you might imagine. So that's why I compared ourselves with other word embeddings approaches. By the way, with the BERT, it's just a 1% difference. And as you can see, we are above state of the art at the moment. And when you do the same with the Glove, which is free word embeddings, Glove 6 billion word embeddings, it's still very close to state of the art, which means that you can safely use Glove 6B word embeddings, even you are not a licensed user. So you can just plug and play, like use this one, and you can use this one with your own clinical data, but we always suggest this one if you want to get better results, because there are sometimes more than 5% differences. Okay, so these are all the benchmark data sets, like more than 10 different benchmark data sets. All the other researchers are competing against, and the bold ones are the one that we already bit. So how NERDL algorithm works in Spark NLP? It's character-based, CNN, by LSTM, and softmax layer actually. We also have CRF approach, which we call NER-CRF, but I'm going to cover NERDL version today. The only difference is we are using softmax layer at the end. On the CRF, we are using CRF layer. I have a blog post about this in Medium, like name identity recognition in Spark NLP with Bert. So you can just read that. It covers everything that I'm talking right now, maybe less than this one. So basically, our goal in our algorithm, we create 3 different features from each sentence. This is a sentence-wise problem. In original paper, they were also using part of speech as a feature, but we don't use. So we take the one word, one sentence, and then get token, each token. So this is the word features. Word features, like we get word embeddings of each word. So this is the first, like this one input comes from words input, which we call it more words input, like tokens. Each token is represented by word embeddings. And then the second feature is casing feature, title case, lowercase, numeric, because as a human, when you look at a chunk, a token, if it's all capital, you might see that this is something different than the regular text. So these are important features for the machine learning models as well. So we use this one as a casing input. We concat with the word embeddings. And the third one is char by char, like the each character. Each character, like since this is a sequential model, even there is a typo, we should be able to understand that, because the word embeddings might miss if there's a typo or if there's some derivative of the same word, if it's not in the root word. But the character-based CNN architecture is so that we can find what's going on before that chunk, what makes that chunk like cancer entity, given the letters before and after. Okay, so we conquered all of them. We have the character embeddings, 10 dimension, we have word embeddings, we feed all of them, and the casing features, we feed all of them to by LSTM layers, and then get predictions on the softmax, and then in true-back propagation, we train the model. So assume like this is a one single word token health. So we get the character embeddings through CNN. CNN, as you know, CNN is like convolutional neural networks are mainly invented for computer vision problems. But it turned out that they are very useful when it comes to text classification purposes as well. See, in CNN, you know, like we try to find the, using through CNN layers, we try to detect some features at each layer, like the shape features, like the human features, etc. Like each layer is responsible to extract some patterns from that image data sets or vision, computer vision data sets. And so in how would CNN play well in NLP domain? It's just like treating, instead of pixel, we are treating each token, like each character or each token. If you apply in like a token-based CNN, it could treat each token. So it just try to like big gram, n-gram, like 3 gram, n-gram, etc. You can just find the pattern by using 1D, 3D convolutionally. Okay, so we just fit this sentence and then create all these features, tokens, casing, and character features. And then, this is more important, every token has a label. This is called, like this is actually, NER, name data recognition is a multi-classification problem actually. So we try to find the label of each token. That's the purpose. That's why we are creating all these features. What makes this token O? O means no entity, so no defined entity. This is company entity. So X, Y, Z, private, limited work. So this is 3 gram, like the first token, second token, third token. It all belongs to the same company entity. So we have representation in CoNNL. We should call it bioschema. Let's talk about that one later. But at the end, we try to predict the label of each token given all these features. And then when we do some like classification report, we just compare each token by itself, like the prediction versus ground truth. There are also some strict evaluation, which means that what if the tokens match? Like there are 4 tokens, 5 tokens, but model was able to predict half of them. In strict evaluation, we check the chunk matches, like X, Y, Z private limited. So right now in the prediction, we missed that like we missed that first token. The model was able to predict the second and the third one very well, but it missed the first, it failed. In strict evaluation, we assign 0 for this prediction because it failed on the entire chunk. But in flex evaluation, we give like 66 out of 100 because it's able to predict correctly 2 out of 3. Okay, this is how we measure the effectiveness of our NER models. So what's the input format? Input format is CoNNL 2003 we are using. It's called bioschema. We support other format as well, but let's just talk about this one. It's much more understandable when we talk about this slide. So in this format, every token lives in one row. There is a space between sentences, and then each token will get some label. In this format, there is the second and the third columns, which we are not using, but it's a part of CoNNL format. So you can just put any placeholder over there if you want to train a model in Spark NLP. Because as I just said, we don't use part of speech, but there's a big but over there. If you are using NER CRF algorithm in Spark NLP, it uses part of speech. So you need to create those part of speech as well. If you are not using CRF approach, but you're just using softmax approach, which we call NERDL, you don't need part of speech. So every token given its position in that chunk gets some labels, like to let the model know that if it's the beginning of a chunk or inside that chunk. Like B-per means that John J. Smith. Like John is the beginning of that person name, that John J. Smith entity, like a chunk. The entity type is person. So we say that, okay, it starts with John, and then it's like the J dot Smith follows that. So they are all I, and then O. So there is no entity here. There is a Washington here, this B log. So there is no second part of the Washington entity. So don't need to add any other I log. So this is how we prepare our NER input data set CoNNL format. In annotation tool, you just select the chunks and we export it as a CoNNL format. So it's very easy. You don't need to deal with. But sometimes you find some data set and then create all these rules by yourself to prepare your own data set. Which for the last few months I have been trying to convert all these medical data set into CoNNL 2003 format because they are all different. They are all in different formats. But it's just like a few if cases and the for loops that you can just easily do in Python itself. Like this one, like John Smith lives in New York. So John Smith is a person entity. And the first one is John. The second one is Smith. So it's I-per. The first one is B-per. So these are 2 different classes. The model is trying to assign B-per to John and then I-per to Smith in the prediction. And then our NER converter in the same pipeline combine these 2 if they belong to the same chunk, same entity, and just the tags by and I tags are different. So enough talk. So let's just see how it works. We just take our data, read our CoNNL reader inside Spark NLP. You just have one TXT file or CoNNL file. It can be any format, like just token, each row, and then space between each sentence, and then label per token. A simple, very simple format. We read it with our CoNNL reader, and then the CoNNL reader creates all the required supporting columns, like a sentence, token, part of speech columns, by using the CoNNL dataset that we just feed in. and it creates Spark data frame because we are going to train the model in Spark environment. So you just feed TXT file or any other format, and then this one creates one data frame by parsing this CoinNL dataset. And then you can select any word embeddings from our Spark NLP library, or you can use your own embeddings. If you have some word embeddings trained in Jansim, you can just feed into Spark NLP word embeddings module and then fit on empty dataset, and then it would be a fitted word embeddings module from now. And then, which means that right now we have all the features. We just fit it into NERDL approach. In NERDL approach, we create the character-based features and the casing features as well, and then fit the model to our network. So this is how it works. Everything that I just talked, like the training, how we do the training in Spark NLP is this. So we take the data set, like we start the Spark session, we read our data set. This is just a simple CoinNL file, TXT file maybe. We select some embeddings. I select Bert embeddings here, which means that it's going to assign Bert embeddings, 768 dimension Bert embeddings for that token given the sentence it lives in, because the Bert embeddings and Bert and Elmo are context aware, you know. The same token would get different embeddings given its position in a sentence. So, and then this is our algorithm. So there are many other parameters that you can tune here, like the number of epo, learning rate, decay rate, dropout rate, etc. You can select here. You can even say, this is my test set, this is my train set. So give me the training, give me the validation and test metrics after each epo. You can just, I'm going to do that in Colab right now, by the way. You can just set it here as well, and then it will give you the metrics in logs. And then I fit, and then training starts on the driver node. So you can do this training in Colab without installing anything. Everything's already there. So, and we have a blog post about that. You can just follow the same. We have another webinar that is, I shared the link in that blog post. And we have some repo that you guys can just plug and play. Some like Spark NLP workshop repo. So let me show that to you. So let's see. So Spark NLP workshop is a free repo. We do some certification trainings from time to time. And you will see under that repo, you will see tutorials folder and certification trainings folder. Healthcare and public. Let's get inside public one. And then you will see all these notebooks. When you click on anything, let's click on this one. And then you can open it with Colab. I right click, open in new tab, and it will open in Colab here. So it's already, so you don't need to install anything on your local. So this should be already here, but I think the session died. So it's not a problem. We can just do everything again. So let's start coding up. But at first, I want to answer some question. Let's see. Okay. Okay. What do the light blue and other colors signify? This is for the Spark NLP module slides. I don't understand the question. Yes, I already covered the use cases. Spark NLP can you based on data frames. You can also, since this is a Spark, so you can also use RDDs to do some basic cleaning or some transformation. It just, when you are done with your transformation, you can just create a data frame out of your RDD. So this, and my article is also shared here. Okay. Okay, now let's train a model. I think there is no other questions. I assume that you already see my screen. Now I opened that Colab by right clicking. I already shared that blog post here. So the first cell is The first cell is just setting up the environment for Spark in Colab, because in Colab, every time when you have a Google account, every time you start a session, it starts from scratch, like a clean EC2 instance, like it's like a cloud instance that you can install anything. But it's specifically designed for data science purposes, so there are already some pandas, sklearn libraries installed, so you don't need to install again and again. So all you need to install is Spark NLP and PySpark, because it's PySpark installed the Spark itself, so we need that. And it should, and Spark works on Java 8, so it's the issue with the Spark, not the Spark NLP. So it needs 8. So okay, it's getting done. So any other question? Let me see. Can you talk about some real world use cases? So I think I already covered. We have a clinical data set, but we can also train that one if you want, but I don't think we have a time. But when you go to clinical folder, like healthcare folder, you will see the clinical name data recognition notebook, which I'm not going to run today, but it's same, but it requires license. You can just ask for trial license from Johnson & Labs, by the way. They give you 1 month free license that you can use everything for free. So there are some clinical NER data sets here, like this is NCBI disease data set that you can use. But it might be like we might not have a time to do this. Maybe we have time, we can just change the data set and do that training. So if we start the session with GPU true, let's not start with GPU true, because in runtime you can select like change runtime and you can select GPU. Let's do that. Okay, so it's already GPU selected on Colab, so I can start my Spark session with GPU true. Okay. When we do this on the backend, actually, we start a Spark session with some default parameters, like a default driver memory or Cairo serializer, max buffer limit, etc. We have some default limits that you can just check Spark NLP library init file for that. But instead of doing that, this is just running PySpark start session and with GPU support. Let's run that one. When you do this, it's going to download some jars into your environment. Jars mean like, since this is written in Scala, it needs to download the logic, all the algorithms from the repo into that Spark session. So there will be a jar downloaded. So you don't need to deal with it. But if you want to change some default configuration, you can do this. So my NER article already explained this one, or there are many other articles in Medium that could explain this issue. So my Spark session is already on. This is Spark NLP 2.5.1. And Spark itself, like Apache Spark itself, is 2.4.4. By the way, Apache Spark 3 is already on, which we are going to support later. So let's download to CoreNL 2003 datasets. CoreNL 2003 dataset is like a person, location, organization entities. So let's just download them from our repo. I just downloaded train and test set. So it's here. So let's see insights. As you can see, I just downloaded and I see in my local folder here, these two data set. And when I read it, it's just a basic TXT file. It starts with this line. It indicates that the document starts right now. And then I have sentence, space, sentence, space. And each sentence is split by tokens and then label itself. So EU is a B organization, German is B messengers, etc. So which means that this is already a default benchmark dataset, CoreNL 2003. So when you want to have your own dataset, you will prepare something like this, as I explained in the slides. So Now it's time to read this into Spark. So as I mentioned before, I will just read this with CoNNL Reader, and then CoNNL Reader will just create all these columns for me. So right now I just feed one txt file, and it tries to create all the other columns, like parsing all that CoNNL file. So it will end up with all these columns. So I fit, like you will see some data frame with all these columns. These are called struct columns, so which means that every column has some metadata. So if you want to reach the beginning indices of a token, you can just use token.begin and then access that one. Okay, the importing is done. So I gave one single txt file, and then it produced all these columns. So the label columns is just the label of each token, and the token columns tokens themselves. So we also have a text column, which is very useful. So you can see every sentence from that CoNNL file, etc. So at the end, when you print the schema, you end up with all these columns. Okay. So if you want to reach the sentence indices, you can use sentence column, and then it's metadata. And if you want to see which token belongs to which sentence, you can also use that one, that token column, and it's metadata, etc. So let me see if there is any other question. Let's talk about the questions later on, I think. So we have 14K tokens, like not the tokens are actually, since this is data frame, it's sentence, 14K sentence right now we have, and each sentence is split in token and then labels, so we have 14K rows. Let's see what's inside. Like in Spark, like to be able to use this, of course, you need to know some Spark commands like PySpark. It's very similar to Pandas itself. So since these are all array, I need to zip and then explode, so that I can end up with this table for the visualization purposes. So I just wanted to see like token, each token, part of speech in your label, and starting and ending indices, so that I want to do some analysis, for example. Or this is just a step that I do to see what's inside the data set, to do some visual checks. Or I can just export this and I share with my colleague, right? So I just say that, okay, take the token result attribute, token result attribute, the token itself, and the results are that attribute itself, and then begin and end is some metadata attribute, like start indices and indices of each token I wanted to, and then I assign some column names with the aliases. So when I run this, it's just created this data frame. Right now, this is Spark data frame, so you can just make this pandas data frame by just writing to pandas, right? And then this could be just pandas data frame, and then you can save as a CSV. And let's get the count of each one. Do not need to run this. When we run this, like group by ground truth, we end up with like the location entities about more than 7K. Person entities is more than 6K. There are some I tags as well, because not every entity is one token. There are more than one token per chunks most of the time. For example, B log 7K, I log 1K. So like one, at least one or 1,000 chunk has more than one token. So some of them might be 2, some of them might be 3. So you can just basically say that, okay, just checking the B ones, you can just say you have as many as these entities in your data set. Okay. So you can, and the next step is selecting some word embeddings. So what kind of word embeddings you can select? You can select Glow, Elmo, Bert, but it depends on the dimension that you want. Like if you select some other Glow, like 300 dimension, you will need to use that graph accordingly, because your model, your TensorFlow backend needs to know the size of the input, like the shape of the input. So that's why for 100 dimension, it's already default, so you don't need to create any graph. But if you need to create any graph, you can just come here, public repo. You see some NERDL graph notebook. Let's open that one. When you start the training, if it gives error, if it says that the graph mismatch, you can just run this notebook and then you say that, okay, my dimension, my word embeddings dimension is like 500. Maybe you train your own data set and then train your own word embeddings and you have 500 dimension word embeddings. You can just make this 500. And this is because the model needs to know the length of chars, because we create some char embeddings. So like it's 100 char per sentence. We set this. It will give you the error and then say that if there's a mismatch, use this like number of text 19, like number of labels, etc. Of course, you can just select them. You can create one giant graph, like say 100 text, like 100 class, and then 1000 dimension, and then 1000 charts, but it will blow up your memory because it will just be useless. So you just need to use the respective one. But for this simple training, you don't need to do anything. When you download this one, let's download that one. When you select pre-trained Glove 100 dimension, it will just download 145 megabit from S3 repo, public repo for Spark NLP. So what else you can do? So you can also download this one. It's 300 dimension, 6 billion. Let's see what we can do. This is Spark NLP models repo. And then in here, you see all the models that you can use through aliases like the names. If you want to use 800 billion word embeddings, you can just write this one, and then language identifier will be this one. As a default, it's EN, English. But if you use this one, you need to select XX. So if you want to use Bert, these are multi-language, by the way. So this is, if you have Dutch language, German language, you can also use this one. There are some English language specific, of course, like Glove 100 is English language specific. So if you want to also know which NER model that you want to use, we'll usually come here. For example, these are for clinical purposes. So for example, I come here and then I say, okay, I have a DNA data set, so I want to use NER cellular model. So it will just use, it will just extract cellular entities from your data set. If you want to extract diseases, you can use this one. If you want to extract some clinical events like admission, discharge, etc., you can use this one. Everything is plug and play. So now I have 100 dimension Glove embeddings. As you can remember, right now I have CoinNL dataset. I have like in CoinNL format. Right now I got the word embeddings. Now I can fit this into any RDL approach. But I also want to, since I also have a test data, I want to also get metrics from my test data set after each epoch. To be able to do that, I need to, because in the prediction, we need a word embeddings as well. After each epoch, model will try to predict everything in test data that I'm going to point out in this block. So I need to write it as a Parquet file after transforming through Glove embeddings. In Spark, there are, as you may know, like a lazy and eager evaluation. Like when I just run this cell, it doesn't do anything actually. It just wrote that graph. And then when I apply some eager evaluation, like write, like collect or show, it will try to implement all graph. So when I just run this, it didn't do anything actually. It just said that, okay, something happened. Some transformation needs to be done. When an eager evaluation function like writing is called. So right now I'm trying to write this to the disk after. So right now there is the Glove embeddings are being appended to this data frame for the test, by the way. This is train set. So we have a similar train test data set that I'm going to evaluate my model on. So there will be a word embeddings column here. So that's why, right? And then I'm writing to the disk so that the model can check that disk and then evaluate, like get some predictions out of that. So it's taking some time writing, like, because it's trying to get word embeddings per token, and then writing to here, and then sometimes Colab might be slow, depending on the region or the computation resources. So let's talk about the main block. We start with, like, we say the model that this is NERDL approach. We say that, okay, use the sentence, token, and embeddings column from the previous steps. We already have token and embeddings and sentence, which is created, this two created by CoNNL reader. I added this here by calling this. But right now, since I'm going to use this inside the pipeline, I'm going to use embeddings just before this one. And it's here. So which means that I'm going to use them inside the pipeline. So I'm going to say that, okay, Glove embeddings will be in the same pipeline with NER tagger, which is the NER tagger. So it will have embeddings, etc. Because its output is embeddings column. In Glove embeddings, I say that take the document and token as an input and create embeddings column per token. So the model will know the position of each token and then the embeddings of that token to train the model. So we wrote the test data to this. This is optional, by the way. If you don't want to spare some test data, you can just skip this one. You can still get some validation metrics after each hypo, but I suggest that you do this to see if your model is overfitting or not. Let me start the training so that I can talk more while the training runs, because it will take, let's just train like 2 hypo to get some decent metrics. And let's start. So I can still talk while the training. I like the training not started right now. I'm going to go back and then talk about this model. So it takes sentence and token and then embeddings column as an input inside the same from the pipeline, and then using the label column as a target column, and then give the prediction in the NER column. And then I can select train to hypo. I assume that you already know what hypo means, so I'm just going to skip that. But it depends on the use case. And usually in NERDL, even on the largest data set, the 10 hypo is usually enough. Yeah, according to my experiences for the last few years, all these projects, I see that after 10 hypo, they usually stabilize. So you can always get better results like 30 hypo, etc. It's just a matter of like a few hours stuff. But 10 is like usually in half hour, you can train a 10 hypo for this model. If you are using GPU, it's much faster option. Learning rate, we have some default learning rates, and this is decay rate, like for the scheduled learning rate. Instead of using fixed learning rate, we decay the learning rate on a schedule. Batch size, I set large batch size right now, but I never do this. Since I wanted to finish it like in a few minutes, it will take 5 minutes to finish. I think just 2 minutes passed, so we have 3 to 4 minutes left. During this webinar, I'm just selected as a 512. So, but usually I select 3264 because everything changes when you change the batch size, because the loss is calculated given that batch. So if you feed like 500, it will just feed right now 500 sentence at once. It will, like the memory requirement will be very high. It's the first thing. And the second thing, the loss, if you have some many false positive and then the model is not trained well at the first few hypo, you will get large loss, and then your model will try to reduce that loss, which will take, of course, it will be faster than small batches, but it will not be representative in the real world, because in real world, we don't feed 512 batches at once. So I say that, like, take the 20% as a validation split and then, you know, we have test set, validation set, and train set. Right now I feed train set, and then I said that use the 20% of the train set as a validation set. so that the model will use this validation split to tune its hyperparameter. There are many other parameters that we don't see right now. And then we use test set, which is unseen by the model. At the end, we get some metrics. Or after each epoch, we get some metrics. But it's not still seen by the model. It's just seen during prediction. I'm talking about the test set. So these are some log parameters. I want to say that give me extended, like enriched logs, and then give me the output logs as well. When I say this one, it will create an annotation logs folder in your local file, local folder, local directory. But you can also set, okay, give me the logs in that folder. So I just wanted to get the logs here inside the same folder, which I'm going to see here. As you see, my model is being trained at the moment, and the logs is here. Like since it's not finished yet, I assume that the first epoch might be finished already. Like let's double click, but it will try to download, so I'm not going to do this. I want to open it here. I don't want to download. Let's wait it till it's finished. So here, I wanted to say that get me the test set predictions, test set metrics after each epoch by using this test data set, which I already wrote to the disk, as you may remember. Like here, I wrote that one here. So I usually, in practice, I usually create the test set beforehand and then write to the disk with the word embeddings so that I would check, because in Spark NLP, we cannot just pause and resume the training, as you may have experienced with PyTorch or TensorFlow. Since this is like the training lives in Spark, it might be a trade-off at the moment. We will try to make it happen later on, but not right now. You cannot just stop the training and then resume, but you can just train 10 epoch and then check the logs and then see, okay, your model is doing good, because you will be able to see, you will get to see the validation metrics and the test metrics. So you can just see how it works, how it trains, how it learns, and then you can say, okay, 5 epoch is enough, or 12 epoch is enough. And you will just understand how your model is doing on test set and validation. So, and then I create a pipeline. This is a PySpark pipeline. I say that use glove embeddings and then use the output of glove embeddings as an input in NER tagger. NER tagger is this one, NER DL approach. The output of word embeddings is embeddings, so it will be used as an input here. And then now I stack them together and then have one single pipeline. Now I can get the prediction. When this is fit, it will be like a trained model that you can save to anywhere. Since this is pipeline, you can just save the second stage of the pipeline, which is NER tagger. You don't need to save this because it's already there. You can download anytime you want. So in prediction, you can just do the same and use the same word embeddings in the prediction as you can do in a machine learning model. So you need to create the same features while prediction, because since you created those features for training, you need to do that. Okay, 6.5 minutes, 2 epoch. Okay, 2 epoch, large batch, which is not optimal, but I just did it anyway. So we will have just a mediocre performance, maybe less than 50%, because it's just 3 epoch and 500 batches. So if you train it 10 epoch with 64, it will take like 40 minutes or something, and then you will get about 90%. So let's see where it's saved. When you check your local folder, you'll see that this is the folder that is just written. Right now it's written. So I can just cut this one and then see inside. Okay, since right now it has 2, like it has 1, you see it doesn't work because I'm trying to call the previous one. Let's copy paste this one. It's coming from previous session, and read this one. Okay, so I have 2 epoch. After each epoch, I have the predictions from test set. So what happened at the first epoch? First epoch is doing really bad, and then evaluation matrix, validation matrix, it started to learn something. let's say 16 macro, 25 micro. We usually use macro, by the way, for the NER because it's just the average, simple average. Micro is weighted average. So if you have some majority class and you also want to get better results on the minority class, that's why you need to check macro average, not the micro or weighted. Okay, so after first approach, this is the matrix from test. As you can see, test metrics and validation metrics are doing really well. Not well, but same, very quite similar, which means that the architecture itself was, by the way, after training more than 100, maybe a few hundred models, what I see is that this model is hardly, like rarely overfit. So which means that you don't need to deal with overfitting. Of course it can. If you by mistake, there was some data leakage from your test set to your training set, you may end up with really good results on the test set, and then in real world you can mess up. So that's why I usually check the duplicates. Even though there is no duplication, inherently there are some duplications. There's another pro tip. What does it mean inherently some duplications? In clinical text, for example, there are some sentences which are copy-pasted most of the time, which means that even though there are different documents, when you get sentences, you may end up with many repetitive sentences. And that might mislead you because it might end up in the test set as well. But in real world, it happens. Since it happens in the real world, it happens in the test, it happens in the training as well. So which means that you may need to make sure about that while evaluating your test metrics. So what happened on the second epoch? Model just doubled. So model learned a lot. It didn't still learn something about the second or third token of these two, but because this is still not enough, it's just 2 epoch. And it just doubled in 1 epoch, which is really good. So when you check the test metrics, you see that it's very similar to each other, which means that the model is not overfitting. It's learning. It's running really well, by the way. In 1 epoch, we just doubled. Keep training this one. If you can just do the same, just fire up a collab notebook and then train this 10 epoch and then share your result with us. So, for example, after training like a few more epoch, this is like, let me see. This is the same data set. As you can see, we see many nice results here after few epoch. So assume that you didn't point your test data set. Now you want to get the test metrics. You can just like read your test data as we just do. So I just got the word embeddings. So I have word embeddings column as well, embeddings column for the test data. So I can just transform. Transform means, since this is the fitted model, NERDL, let's see. NERDL model is fitted. Okay, so this can be used to predict something. So I'm just saying that, okay, transform. Transform in Spark language means that like transform. Like we can see the same in sklearn, by the way, like for the scaling purposes. If you say transform, you use some fitted scalar to make some transformation. So we want to predict NER from test data. And let's just check the few of them. Now I have the predictions here. Since this is the Spark data frame, you may not be able to see that. Let's make it better, like cleaner. So when I run this, like just first 3 row, okay? These are my tokens, West Indian all-rounder, okay? These are my ground truth, the second column, BMISC, IMISC, BPER, and these are my predictions. So it's doing a little bit, so as you can see, it tried to predict something better. So for the London, it found London very well. So the Leicestershire, it found that organization very well. So let's see this in very tabular way, which by using exploding and zipping. So cricket ground truth is O, prediction is O. This is ground truth is B org, prediction is B org. So the model, after just 2 epo, even though metric says that it's 50, around 50%, like 50% of the time it's doing good after just 3 epo. Okay, of course there are some wrongs predictions because we didn't train further. So if I want to get the metrics, what I would do is I just used a scale-learn classification report. So I can just get the predictions and ground truth and convert to pandas, and then treat this as like any other scale-learn model. Like, let's do this. So you will see some classification report coming out of scale-learn. So you train your model in Spark NLP and then getting the predictions right now. So right now, all the predictions are created because it says 2 pandas. So this is eager evaluation. So it's right now getting the predictions for each, for entire test set. All these data points in the test set are getting a label right now. That's why it's going to take a while. And then it's converted to pandas as well, which means that it's collected into one single, like right now, this instance, so from Spark environment. So it's now collected into pandas. And then classification report will just these 2 columns and then produce some reports that we can see. So next I'm going to, I think it will take a while to calculate these metrics, but we don't need to see because it will be same as you see here. So it will, but here we don't see O. In the original logs, we don't see O class because it's a majority class and we don't want to see it in the evaluation. But here you will see O's, of course. Okay, so if you have one data set, you can just split your data set by using random split. You can just read one train data and then split like 30% versus 70%. You can create one single data set. Like you can create test and training data and then apply the same steps here. So if you want to save your model, since this fitted, it has 2 stages, borderlines inside the same pipeline and any other. These are all fitted since it gets some text here. So I just can say that, okay, save the second stage because I need this one later on. Second part, not this one because this is already there. I can just pull it from S3 later on. By the way, the prediction is done, and this is my classification report. You can see, like for the O class, it's doing, of course, better because it's driving the entire data set. So for the location and this one, there's no. But right now, weighted average stays at 88%, including O. Right now, I have 88% accuracy, which would be misleading because I need macro average. That's why, which means that I need to train this further. Okay, so right now I have the model and then I saved this. I said that stage 1 can be written to disk. If there is no previous model, you can just ignore this part, save this here. So I can just load this into any prediction pipeline. Assume that I trained this model for days, like I am building a large NER model. Now I want to get a prediction. Like I want to deploy this model in somewhere so that other people can use or connect to some other downstream test. So I just create this pipeline. Like it starts with the same pipeline like the CoNNL reader does. I will say that, okay, get the text column and then do everything one by one. Get the sentence, get the tokens, get the, so Spark NLP would be a little bit verbose and hard to follow at first, but we are also working, we are every day working to make this simpler, at the same time keeping the accuracy and the performance at top. So it will get more Pythonic later on, but still, this is still very understandable, I guess, because we also have many other workshops and workshop repos, notebooks that you can plug and play. If you know PySpark, this is the same actually. It's just you need to follow up this building blocks concepts. So since I used Glove 100 for the fitting the model, I need to use inside the prediction as well. I just put this. So you handle this part and then you say that this is the saved model. Since I saved, I will just load from disk, like in another machine, assume. Now, and then get the converter. Converter means like combine B and I tokens, so that I don't want to see John B name, B person, Smith I person. No, I want to see John Smith as a person. So that's why I use NER converter. So when I do this, I just fit on an empty data frame because everything is already fitted, so I don't need to fit again. And then get the prediction. And then let's get the prediction from this sentence. This sentence, Peter Parker is a nice guy and lives in New York. So I should be able to find Peter Parker as a person name, New York as a location. When I do this, I at first create data frame out of this text and then feed it into my pipeline because my pipeline needs text column. So I create data frame, which has a column name text, and then feed it into my like transform my pipeline because my pipeline can be used to predict something, which means transform. And then when I do this, Peter Parker is a person, New York is a location. Right now it's ready. So you might think that why do we need Spark data frame to get prediction? Because it might look worse. So we have light pipeline concept for that. Light pipeline is, we have another, I personally have a blog post about this, why we use light pipeline, because Spark is good with large data, big data. So it's like a comparison between locomotive and a bicycle. So locomotive, like a bicycle, will be very fast at the beginning when it competes, when it races against locomotive, but it will definitely lag behind when the locomotive gets faster because like the load gets bigger because and this is what happens in Spark as well. So that sklearn or some other non-cluster solutions would be, of course, better like spicy on single machine, on small data. But when you have a big data, first, you don't get to have state-of-the-art latest results in the other libraries, which we already cover every week. Second, you cannot get predictions from your 100 gigs clinical text or any other legal text predictions on a single machine. So that's why we created Light Pipeline. Light Pipeline just removes the overhead of Spark itself and then brings everything into single machine and then use like multiprocessing. So it uses every CPU that you have and then you don't need to create data frame. You just feed string text and then annotate. Since I say that this is my light model, my fitted model inside Light Pipeline coming from Spark NLP. And then now I want to annotate my text, my string. And it just returns a dictionary like this way, E per, I per. Now I have the token per label prediction. So if I want to get like a pandas data frame, it's just a dictionary parsing. You can just parse your dictionary and you can end up with this table. This is pandas table, the pandas data frame. You can just save this. Or you can just use, because if you want to combine your like chunks, like NER span comes from here, NER converter. So if you want this one in the output of the light pipeline, you will see NER span key. So you will use that one to get Peter Parker as a one single entity. Okay, we are done. Let's create quickly our own CoNNL file. I'm sure that you guys have might have some question about how we can create our own CoNNL dataset. What I do is, since I need if I'm not using any annotation tool, if I'm doing this from scratch, if I have just token versus label at somewhere, I just create one single pipeline here and then produce some part of speech tags, etc. So that I can, like this. But by the way, this is a prediction pipeline, not the annotation. Let's talk about annotation. Okay, so we have one single pipeline and I have sentence. So I want to get a CoNNL format from this data set. So I can use the prediction pipeline to do this, right? And then I can change the labels. Or if you already have it, you can just write some for loops to append your own. If you assume that you have some data set like token by label. You can just loop through by zipping and then assign it as the last column and the first like token itself and the last column. And you can get the part of speech from Spark itself or Spicy or anywhere you want. But in Spark NLP, as I told before, there is no, we don't use the second and the third one. So you can just use XX here like a placeholder. It just needs to be there somewhere according to CoinNL format. So you can create your own data set. As you can see, I said that, okay, loop through my sentences, parse that sentence, my Spark pipeline. That Spark pipeline has nothing to do with my prediction, but it can be any pipeline that could produce some tokens because I need tokens. I need part of speech, which I don't know need in Spark NLP. And I need label columns. So I can get that label from predicted model, but this is just for the visualization purposes. In reality, we don't do this. So you can create this one and then write as a CoinNL file. So we are done. Let's see if there's any question here. Okay. I don't see any new question, by the way. Right.
There are no new questions, but there are a lot of questions in the chat.
Okay, I saw it. Are we recording? Yes, we are recording. I assume, Thomas, you already started recording again, or you will just cover the remove the first part. So we will have a recorded session.
Yes.
And then you will. I hope you, because they ask. Great. How glow embeddings are different than BERT? BERT is. Let me open something. Here, let's say another, we have demo slide here. I cover some stuff there, to explain the differences between BERT and. Okay. So we have 4 different: GLOW, ELMO, BERT, and universal sentence encoders. Universal sentence encoders space, so we don't use this for NER, but for the text classification we use this, and it's very powerful, by the way. For the BERT and ELMO is context aware, so it creates word embeddings per word according to sentence it lives in. It's the latest and the coolest algorithm in NLP libraries at the moment, NLP domain at the moment. There are different versions like BioBERT, BlueBERT. We also have BioBERT, by the way, biological, like clinical version of BERT, like here. If you are using clinical, doing some clinical NLP, you use BioBERT or clinical BERT. So for the GLOW, the word embeddings are according to the concept is simple. It's simple as this. Words that occur in the same context tend to have similar meanings. This is the basic idea behind word embeddings. So GLOW, just by building that relationship, like a knowledge graph, by training, it tries to find, assign some vector per word, regardless of sentence it lives in, because it doesn't check the sentence. One word will always get the same embeddings. You see this example, it says that what's the embedding of the word stick. So sticks word can get the same embeddings every time in GLOW. But in ELMO and BERT, it depends on the sentence it lives in, because BERT, it's a huge model that used by masking some words at every iteration, so that it's changed its embeddings each time. So I think it's not a part of this discussion. You can just Google it. You can find many different articles that can explain this thing better than I do. So how does machine learning approaches compare to rule-based approaches? Of course, machine learning approaches are doing better for this specific NER models. But when it comes to relation extraction, I can say that not the rule, but the machine learning's doing better than deep learning approach. So you can create some features in relation extraction models, by the way, by handcrafted features, and then train some random forest, and it will beat deep learning models. Because Relational extensionship is a hard problem in NLP still. For the rule-based, it can, but rule-based, you need to write thousands of if cases. You are not able to be able to write a perfect rule, you need to see every cases. But in real world, it's quite possible that you will miss many other edge cases. Another question, did you say you recommend using a subset of the training data for validation? In other words, the same data is used for two things. For validation, we chunk 20 or 30% of the training set as a validation set so that the model just use 70% to train, 30 or 20% to validate itself, to tune its parameters, to find its way through while training. This is the purpose in validation. So of course I will chunk some validation tests. Sometimes we also do some cross validation. Like every time we split some other portion of the same training set. But for the training, we don't use validation. Validation is just calculating the loss after each epoch. So during that epoch, model just use training data. This is the concept in machine learning. Okay, I think I'm done with the questions. And we are done with the time actually. So if you have any other question, I can answer.
Awesome. Well, thank you so much, Veysel, for coming, and thank you for your time, and thank you everyone else for joining us. We just got a question. Where can we have the slides?
I can share the slides later on with you guys, and then you can share with the community.
Yeah, that works. We can just go ahead and post that on any of our social medias. Sure. Anyways, thank you so much for giving us your time. We really appreciate it. Our next talk is going to be on this next Friday, another talk on AI in healthcare and just how it can be implemented. We're going to have a panel of about 4 different speakers. We've been having talks like this for the past 3 weeks, so this will be the 4th in a series. It's very interesting. Please check it out. I dropped the link in the chat, and I also dropped the link to this YouTube video in the Zoom chat, so you can find both in there. Have a good rest of your day, everybody, and thank you so much. Can't wait to see you at the next one. Have a good one.
Yep. One last question, maybe. Dave keeps asking that question, I think. Let me explain. In the slides, I shared test versus dev. Test is getting the metrics from test data set because every competitor in that competition, CoNL 2003, needs to use the same test set. So it's the test F1. Dev F1 is the one that I just shared after validation. Validation means like dev means like validation. So this is the validation metrics after each one. So it's the validation, like the chunk 20% from train set, not the test set. So but it's very close to each other, as I just mentioned before. Okay, we are good to go. Thank you. Thank you very much.
All right. And if you don't see the links right now, you have to scroll up in the chat. All right, I will just resend them.
Okay. Yes.
But yes, have a good day.
Yeah, you too. Have a good day, everyone. Bye.